let's start. Thank you everyone for joining the meeting. It's our pleasure to have Carla Sederbaum from the University of Tübingen. She will talk about explicit minimizing sequence related to Romanian Penrose inequality. Thank you, Carla.
Thank you very much, Agil. Thanks for everybody's patience with the technical problems. I hope it'll work all fine now. And of course, thanks for the invitation and for everybody to join at whatever convenient or inconvenient times of the day. I'll speak about explicit minimizing sequences related to the Romanian Penrose inequality, and all I'm going to talk about is joint work with Armando Cabrera-Pacheco. So let's start with discussing the setup and some relevant definitions. So all I'm going to say is going to be on three-dimensional Romanian manifolds, and they're all going to be smooth, and they're going to be asymptotically flat, and whatever notion of asymptotically flat Riemannian manifolds you have in mind is fine for the purpose of this talk. As we'll see later, doesn't matter how fast you want your asymptotic flatness to be, and it has non-negative scalar curvature everywhere. So that's what I'm going to assume about the interior of the manifold, and then it will have an inner boundary. And this boundary is going to have an induced metric G to fixed notation, and to make sure that the metric smoothly induces a smooth metric on the boundary. It will be minimal inside the manifold. So it'll be having mean curvature H equals 0, and it will be diffeomorphic to S2, and in particular connected. And moreover, we'll assume that it'll be strictly in some settings or weakly outward minimizing, which means that if I consider any two surface sigma 2, which is homologous to this boundary in the manifold, then I want sigma 2 to have strictly or larger or equal to the same area as the boundary. So any comparison surface which is homologous has at least the same area, then we say it's weakly outward minimizing, and if everyone has strictly more area, it's said to be strictly outward minimizing. And for the purpose of this talk, we have to be precise about this distinction. And here's the favorite example that you should keep in mind, and that I'm sure most of you will be very familiar with. It's the spatial or Riemannian Schwarzschild manifold. So it's the manifold here in this example is R3 minus a ball of radius 2m around the origin, and the ball is closed, and m is a positive parameter, usually called the mass. And the metric, and I'll identify this with the radius interval 2m infinity cross S2, where the angles live. And the metric on this is going to be denoted by gamma m. Looks like dr squared divided by 1 minus 2m over r plus r squared g star, where g star is the canonical metric on S2 of area 4 pi. And the properties that I described in the general case all apply here. This metric is even scalar flat. And it's of course asymptotically flat in whatever sense of the word you prefer to use, of mass m, ADM mass m. And the inner boundary is well known to be a minimal, even totally geodesic surface, which we call the horizon. And it's strictly outward minimizing according to the definition I gave earlier. And also the area, so the metric induced on the inner boundary will be 4m squared g star, where g star, recall, was the canonical metric of area 4 pi. So that's the induced metric, and of course the boundary has area 4 pi times 2m squared, which gives you the famous 16 pi m squared that you may be familiar with from the Penrose inequality. So that's the next thing we will look at, will be the Romanian Penrose inequality. Which I'll abbreviate in what follows as the RPI. And it was proven by Husken and Ilmanen and by Bray independently in the early 1990s. And I want to state it here as saying that M3 gamma is as above. So non-negative scalar curvature, asymptotically flat with suitable inner boundary. And of course, I want the boundary to be minimal, but I also want the boundary to be strictly outward minimizing in the sense I defined above. And then this Penrose inequality, this Romanian Penrose inequality, celebrating the recent Nobel for Penrose, maybe here in this talk, says that the area of the boundary divided by 16 pi, if you take the square root, is always bounded above by the ADM mass of the manifold. With equality, if and only if, we are in spatial Schwarzschild as described in the example, and the mass parameter of the Schwarzschild is exactly the ADM mass of the manifold that we're looking at saturating the inequality. And if we say it's equality, of course we mean it's isometric too. And if we say isometric too, we of course mean it's isometric to the entire Schwarzschild manifold, including the horizon where the coordinates degenerate. So we have to smoothly extend the Schwarzschild metric to the minimal boundary here. And the Penrose inequality is a very fundamental result of geometric analysis and mathematical relativity, and can be viewed as some kind of quantitative refinement of the celebrated Riemannian positive mass theorem, which was proven by Schoen and Yau and by Witten independently in the 1980s. And the question I want to deal with today is the following, is the question of stability of the Riemannian Penrose inequality. And the question, yes? The question? No. Okay. So the question is as follows. Somebody's having their sound on, and I hear an echo. Suppose M3 gamma is as above, and has almost saturated the Penrose inequality. So it has ADM mass bounded above by the lower bound that the Penrose inequality asserts, plus some small positive epsilon. What do we know? Do we know? And in particular, more precisely, do we know that M3 gamma has to be somehow close in some useful, suitable topology to the saturating Schwarzschild example? Is M3 gamma close, in quotes, to Schwarzschild in some topology? So before I'll tell you what the result is that Armando Cabrera Pacheco and I proved, let me tell you what is known about this question before we started working on this. So we have known evidence both for and against this stability. So let me start with the evidence for the stability. So for a statement of the form, we have a sequence of manifolds that almost saturates better and better the Penrose inequality. So the epsilon on the right-hand side of what I just wrote here will be smaller and smaller and smaller. And then evidence for stability would mean that the sequence M, K, gamma K approaches in some topology the Schwarzschild metric, or something that's isometric to the Schwarzschild metric. So we have evidence for stability. But we also have evidence against stability. And I'll quickly give you ideas about what we know about both, and I'll try to use blue for stability and green for instability. And for stability, the first result I'm aware of is a result by Dan Lee and Christina Somani from 2012, which is in spherical symmetry, and says that under suitable conditions that I'll not detail here, except saying that you have to stay away from horizons, from the horizon, from minimal surfaces. They get stability in the Somani-Wenger intrinsic flat distance. So that's a suitable topology, or a debatably suitable topology, in which you can get stability in the class of spherically symmetric manifolds or current spaces as a generalization thereof, if you somehow are in a region that's suitably bounded away from the minimal surface at the inner boundary. In that region, you will get convergence in this intrinsic flat distance. There is a more general result by Brian Allen from 2018, which says that assuming that you have a sequence, let me write it down, a sequence of MK3 gamma K with or saturating the Penrose inequality in the limit, such that all the members of the sequence have a smoothly foliated by an inverse mean curvature flow. And these inverse mean curvature flows are uniformly controlled in K in a certain way. Then we get stability, so convergence to Schwarzschild in L2 on compact sets. So the reason why the inverse mean curvature flow comes in here is that the Huisken-Illmannen proof of the Riemannian Penrose inequality uses a weak version of the inverse mean curvature flow, which is really technically hard to deal with. So Brian assumed the existence of a smooth inverse mean curvature flow, which has uniform control, and this uniform control on the smooth inverse mean curvature flow allows him to prove this stability in L2 on compact sets. So this we know on stability, the special case of spherical symmetry, if you stay away from the horizon, or if in this more general case of manifolds that have a smooth inverse mean curvature flow, but assuming that it's uniformly controlled, in particular near the horizon. So evidence for instability. We also have from the paper by Lee and Somani, same paper. And maybe shedding a little bit of light on the spurious staying away from the minimal surface condition that I mentioned. Again, this is in spherical symmetry. And they find a sequence of examples that converge to the following object in Somani-Wenger intrinsic flat distance. This is just a round cylinder. And then you attach to it a Schwarzschild. all the way down to the minimal surface. So you take your usual Schwarzschild all the way down to the minimal surface, and then you just continue as a round cylinder. That's what the limit looks like of the sequence that converges to this limit in Sormani-Wenger intrinsic flat distance, which shows an instability of the Penrose inequality, because this limit saturates the Penrose inequality, but is not isometric to Schwarzschild, because it's really Schwarzschild with a cylindrical neck attached, and they can prescribe the length of this cylinder in advance of the limit manifold. So I should write Sormani-Wenger intrinsic flat distance here to remind you of the topology in which this lives. I should say one more thing about the limit. The interior boundary of this limit, so at the inner end of the cylinder, is a minimal weakly outward minimizing surface, but because all the cylinder leaves of constant parameter or height, say, in the cylinder are all minimal surfaces, all of the same area, it's only weakly outward minimizing and not strictly outward minimizing. Of all these surfaces, the only strictly outward minimizing one is the one where the cylinder attaches to Schwarzschild. So in some sense, this instability that they find, the long cylinder hides behind the outermost, the strictly outward minimizing surface, which is a pattern we're going to see again. And of course, their limit is still asymptotically flat because it's even exactly Schwarzschild outside some compact set. There is another evidence for instability coming from a paper by Christos Mantroulidis and Rick Shane from 1915. And they perform a construction which doesn't use a specific topology, but they just perform a construction, which I'll explain in a second, which allows you to prescribe a non-round metric on S2 and include it into a spacetime that will, a Romanian manifold that will eventually look like Schwarzschild and will satisfy all the conditions of the Romanian Penrose inequality. And you can do that such that these manifolds almost saturate the Penrose inequality. And because they almost saturate the Romanian Penrose inequality, there's a question of they cast some doubt on stability of the Romanian Penrose inequality because the interior boundary is far away from round. So there's very little hope that there should be a topology where these manifolds converge to Schwarzschild. But I'll write something and be more precise now. So for any metric G0 on S2, where the first eigenvalue of the following operator minus Laplacian G0 plus K G0 is positive, where this denotes the Gaussian curvature. So for any such metric on S2 and any m bigger than the area of S2 with respect to this metric divided by, 16 pi. So that would be the threshold for the Penrose inequality. There is a smooth M3 gamma such that all the above conditions are satisfied. So the boundary is minimal and strictly outward minimizing and so on and so forth. With ADM mass equals this M that we prescribed. So because the boundary can be far away from round, subject to this eigenvalue condition, somehow the manifold they construct will certainly not be close to Schwarzschild in any reasonable topology, or so the conjecture. And so probably this indicates some type of instability of the Romanian Penrose inequality. So whenever I heard a talk about this result, either by Christos Mantroulidis or by any of the people who did follow-up work on this, there was an immediate question from the audience. So can you construct with this method a sequence of such extensions, as they call them, with masses going to the saturating value in this inequality here, in this Riemannian Penrose inequality here, and such that one can control the geometry of this extension along the sequence well enough so that one sees that they do not converge in any reasonable topology to Schwarzschild. Well, that's very suggestive, but a lot of things could happen in such a limit. The construction things could blow up or shrink to singularities, or lots of things could happen. So the theorem I want to present today is an answer to the question, can you construct a sequence from this procedure? From this procedure, which shows instability of the RPI, and hence extends the result by Somani and Lee and Somani, sorry. Okay, so why isn't this immediate? I mean, I haven't told you much about the construction. Maybe you've heard something about this construction somewhere, but the point of this construction is that in some sense, you can consider it as very qualitative. Okay, so there are lots of arguments like then you find some parameter with which you can rescale something, and then you can achieve the existence of such an object. But if we want to construct a sequence of such objects that converges in some topology to some limit, then we need to be extremely careful. In all these existence statements, we need to be very precise. How do we pick all the parameters you need to pick such that you get convergence in a suitable topology to a suitable limit? And that's the new addition that I want to talk about today. So here's the theorem by Carrera Pacheco and myself, and I'm hopeful that it'll be on the archive this year. Let G0 be a metric on S2 and smooth, of course, with the same eigenvalue condition that Mantelidis and Chain impose. Then there exists a sequence of smooth Riemannian manifolds or rather I should say metrics, gamma k, because they all live on the same manifold, which is nothing else but a half line cross S2, and the parameter in this half line is going to be called S, such that the boundary, which of course is 0 cross S2, sits inside M3 for any of these metrics gamma k as a minimal strictly outward minimizing surface. Together with its induced metric gk, the boundary is isometric to S2 G0. That's the metric we started with, that we prescribed. M3 gamma k is asymptotically flat of mass mk. And has non-negative scalar curvature, of course. And the masses mk converge from above to the threshold you would expect, namely the area of S2 with respect to the given metric divided by 16 pi, which is of course the same thing now as the area of M in any of these metrics gamma k divided by 16 pi, and which I will call M infinity suggestively. Okay, so we have these from the Mantelidis chain construction with suitable parameter picking and also some more suitable adjustments that I'll talk about later. And the sequence is such that gamma k converges to some metric gamma infinity on M3 as k goes to infinity in C1 alpha on compact sets. For any 0 less than alpha less than 1. And gamma infinity is C11 smooth away from some surface of this form. Recall the whole manifold was a half line of S parameters cross S2, so this is just one of these sections. And there it's not C2 on this surface, but everywhere else it's smooth, and there it's C11. And the metric gamma infinity induces a smooth metric G infinity on the boundary, and so the boundary is also isometric to G0. The scalar curvature of the limit is of course non-negative away from where it's not C2. And actually the gamma infinity, if you restrict it to some semi-open interval S infinity, from S infinity to infinity cross S2, is isometric to all of Schwarzschild of mass M infinity. Recall M infinity is exactly the mass that saturates the Penrose inequality for the G naught on this inner boundary, for the area from that. Okay, so let me run you through the long text of this theorem again. We pick a metric on S2 which satisfies this eigenvalue condition. If you're not familiar with this eigenvalue condition, which is related to stability of the minimal surface, you could just think of a positive Gaussian curvature. That would be sufficient as well. Or you could just think of the spherically symmetric case dealt with already by Lee and Somani, which turns out to be a special, I mean, our construction leads to the same result as Lee and Somani's result in case you prescribe around G0. And so for this G0 that you picked on S2, subject to this condition, we give you a sequence of Romanian metrics that have this metric as their inner boundary, and which are of the form a closed half line cross S2, such that the boundary stays the same along the sequence intrinsically and stays minimal along the sequence and stays strictly outward minimizing along the sequence. And all the members of the sequence are asymptotically flat of some masses mk and have non-negative scalar curvature such that the masses descend to some value m infinity, which is exactly the saturating mass for the boundary value we prescribed. And the limit looks very similar to the specific example I gave you in the spherical symmetry by Lee and Somani. It's smooth away from just one surface where it really looks like a cylinder attached to Schwarzschild, as we'll see later. And it's smooth away from there, C11 across it. The inner boundary of the limit is what we expect. The scalar curvature is non-negative where that makes sense. And outside the specific parameter value S infinity, it's Schwarzschild of this saturating mass. So it does saturate the Penrose inequality. And the convergence that we get is in this topology C1 alpha on compact sets, which is extremely strong. And you cannot expect much more given that the limit isn't even C2. Okay, so let me make a couple of remarks. So one remark is, of course, that the limit saturates Penrose inequality. And this is not contradicting the rigidity case of the Romanian Penrose inequality, of course, because the metric is neither smooth, which was an assumption in the Romanian Penrose inequality theorems, nor is the inner boundary strictly outward minimizing. So the inner boundary in the limit manifold is only weakly outward minimizing. Weakly outward minimizing. And not strictly. That's important. However, this surface S infinity cross S2, where the crack happens, is strictly outward minimizing. And has the same area. All S cross S2 have the same area for 0 less than or equal to S less than or equal to S infinity. So in that sense, it looks like a cylinder all the way up to this value at the S infinity. And from there on, it looks like a full Schwarzschild down to the minimal surface. And so at this value S infinity, we have a strictly outward minimizing surface. I will draw pictures in a second. So the fact that the boundary is only weakly outward minimizing is the key to why this is not violating the claim that the only manifold saturating the Romanian Penrose inequality is Schwarzschild or other Schwarzschild family. Okay. So this shows that an instability, another type of instability of the Romanian Penrose inequality in this strong C1 alpha uncompact subset topology, and work by many authors shows that this C1 alpha uncompact subset topology implies, for example, Gromov-Hausdorff, but also the Sormani-Wenger intrinsic flat distance convergence that Lee and Sormani use. So the convergence we prove implies the same type of convergence that Lee and Sormani get in the spherically symmetric case. So this is Gromov-Hausdorff, and this is Sormani-Wenger intrinsic flat convergence. So in that sense, it extends the Lee-Sormani instability result. And relating to the positive result by Lee and Sormani, of course, in the spherically symmetric case, we recover their instability result, and of course also their stability result applies there. But it's also interesting to relate our instability result to the stability result I mentioned by Brian Allen, who uses this uniformly controlled smooth inverse mean curvature flow along the sequence. And we find that our surfaces S cross S2 are actually the leaves of a smooth inverse mean curvature flow in each manifold. In each gamma k, okay? But they're not uniformly controlled near the horizon. So near where along the sequence we have the strictly outward minimizing surface, the inverse mean curvature flow is not flows along these metrics is not uniformly controlled, which allows us to get this instability, complementing the result by Brian Allen very nicely, I think. And of course, as I mentioned before, our proof relies on the Mantelidis chain construction, but not only on their work. So but also on generalizations and refinements of their work by, and I'll do this in alphabetic order, Cabrero Pacheco. Otherwise it becomes too complicated. Myself, McCormick, Miao, and Xie, which they in papers aiming at different refinements or generalizations or applications of the work of Mantelidis chain, they introduced quantitative measures of control in the proof that was rather qualitative initially, and these quantitative measures are things we use as well. And let me just briefly mention, because I don't think I'll have much time to talk about this, that the construction also has consequences and implications for Bartnick's mass minimizing conjectures. very weak ones though. And let me spend the remaining time on discussing ideas for the proof and finally providing pictures. And given the rough start, Agil, could you maybe give me an estimate of how much time I still have?
I think you have 20 minutes.
Perfect. Thank you.
Yeah, 20, 25.
Thank you. So let me be very clean on this. I'm given, as in the theorem, both in the theorem by Mantelidis and Chain and in my theorem with Armando Cabrera, I'm giving a metric on S2, which satisfies this eigenvalue condition. And I'm not going to explain why it's relevant or how we use it much here. And the construction by Mantelidis and Chain that we refine comes in 3 steps. And I want to walk you through each step individually and explain in each step what we needed to achieve to get this C1 alpha convergence along a sequence. So the first one is a collar construction. And so let me draw this. So here, this is my impression of the metric G0 on S2. And I take this metric. Yeah. And I take this metric and put it into some kind of collar. Give more math details in a second. Up to some round boundary. And in this direction, I will use a parameter t, which is 0 here, 1 here. Oops. And it'll be theta somewhere here. And from this theta onwards, everything is spherically symmetric. So how do I construct this collar that takes this potentially highly non-trivial metric G0 on S2 and connects it to a round sphere in this collar-like fashion? So this works in also somehow 3 steps. So the first idea is to use the uniformization theorem. To get a flow G of t for t in 0, 1 of metrics on S2, all smooth, everything is smooth here, such that of course G of 0 is G0 and G of S is t R0 squared G star. G star, recall, is the canonical metric on S2 here, and R naught is the area radius of G naught. In such a way that the area of S2 with respect to any of the G of t's is 4 pi R naught squared for all t. And this eigenvalue condition, that's just a technicality that I don't want to explain here, stays put under the flow. So I get this flow of 2 metrics on S2 that doesn't give me a 3 metric yet, in which G naught sits as a nice inner boundary metric. And then before we construct a 3 metric, we need to do some gauge fixing, which we do as follows, or I don't explain how we do it, but or how Mantelidis and Chain do it. We just apply their result here, such that we have that the area element, not just the area stays constant, but the area element for integration stays constant for all t. This is by diffeomorphisms. This is just a useful gauge. If you want to express this more in terms of flow, properties, then you can write the same thing as the trace of g of t, of g prime of t with respect to g of t being 0 for all t. So you can achieve that, and we just cite that part from the Mantelidis chain. And then you consider a 3 metric, which comes about as follows. The 3 metric at a point Tp, where T is in 0, 1, and P is in the sphere, is given by A squared U of T and P squared dt squared plus F epsilon of T squared G of T, where we have that A is a number, U of T and dot is the eigenfunction, for lambda 1 of the operator minus Laplacian G of T squared plus K G of T. So that's why this operator plays a role here, because we want to use its eigenfunction and exploit it. Epsilon, of course, is a small positive number. And F epsilon of T is a radial profile given as 1 plus epsilon T squared for T. Okay, so using this number A and the number epsilon and the eigenfunction for this eigenvalue lambda 1, for the first eigenvalue lambda 1 of this operator, we can write down a 3 metric on 0, 1 crosses 2, which is now a nice metric. And given the properties of F epsilon, we can see that the induced metric is, of course, G of 0, because that's how we constructed the flow. And we can also compute from this form of the metric per se that the interior boundary is going to be a minimal surface, and also that it's strictly outward minimizing. And now we need to deal with the scalar curvature of this guy. And it turns out that provided A is large enough, then gamma has a negative or even positive scalar curvature. So let me walk you through the picture again. So we take this G0 metric on S2, we flow it to a round metric. Did I put? So this should be for t bigger or equal to theta, sorry. So which will eventually be round after some value theta. So that will be spherically symmetric. So that's a family of 2 metrics on the sphere with certain properties. And then we take this family and put it here, multiply it by this little opening up function, which keeps the inner boundary minimal, but makes it strictly outward minimizing, and warp it, not really warp it, but combine it with a metric in t direction, which depends on this constant A and the eigenfunction. And we do that in such a way that we can see that if A is suitably large in terms of all the other data, including epsilon, then this metric will have positive scalar curvature. Now this is sufficient to show existence of such a color, but we want a family of such colors. So we need to pick A carefully, depending on all the data, including the epsilon. For us, the epsilon will be 1 on this sequence parameter K. Yeah, and we need to pick A carefully in terms of K. And what we achieve is actually that we get it independent, we get a value independent of K, so that all the gamma Ks that we construct this way have positive scalar curvature. So that's the new ingredient, that we need to pick the A so carefully here. Okay, so that was the first step, and I'll show you the picture again so you can keep the picture in mind. So that's the color. And so now in the second step, we'll construct another object that I'll make yellow. So we'll have a step 2. And in the step 2, maybe I will write in blue, but I'll draw in yellow. We take Schwarzschild. the usual Schwarzschild, we reparameterize it so that it lives on the same manifold that I mentioned before and has the form gamma hat m is ds squared plus um of s squared, the canonical metric on the sphere. And this is possible, and it's not possible to write down the explicitly, but it's very well understood. And then we chop it off some value s, which depends on k. And then, so let me draw this. So we have our usual Schwarzschild all the way down to its minimal surface of some mass m, which will later now depend on k. So this would be your usual r equals to mk, which is now called s equals 0. And this is r to infinity and also s to infinity in these new coordinates that you may be less familiar with. And now what we do in the step 2 construction, we chop it off somewhere at s equals sk. And this will of course correspond to some radius, which also r, which also depends on k. And then after chopping it off, we take a little part of it, continue it as it was here, and then bend it inward. So that we exactly, oops, this is not a good picture, at some s equals sk plus some small delta k. From to the right of that, for s bigger than that, we exactly Schwarzschild. While between where we chopped off at this sk and this sk plus delta k parameter, we've bent it inward so that we've obtained positive scalar curvature. Of course, where they match, the scalar curvature decays to 0 so that they match smoothly. All of this is completely smooth, as in the other step as well. So this again is exactly what Mantelidis and Chain do, and all the refinements also do. But what we do now is we do this in a way that we have to control both the sk, so that where we chop off, and the delta k, so the width of the region where we're bending in, so that well enough to get good estimates later on the sequence. And so the yellow part is what we keep, and we forget the chopped off part. Okay. So now we have this blue color that starts with the inner boundary value G0 we prescribe. And on the other hand, we have this yellow infinity region, which has positive scalar curvature and is spherically symmetric near its inner boundary. So it's all, we do all this bending in spherical symmetry. And then in the step 3, we want to create a positive scalar bridge between these two things. So let me first redraw very sketchily what we had. So we had this color. T equals 0, t equals 1, t equals theta. And on the other side, we have this. Now I have to draw through my writing. The Schwarzschild, which is bent inward to some surface where we had some s equals sk here, and s to infinity here. And from here on, we are spherically symmetric. And all of this is spherically symmetric. And here we have this sk plus delta k, so that we have positive scalar curvature here. And we have Schwarzschild here. And so the first thing we do in this bridging procedure is that we reparameterize the color. You don't need to pay too close attention. S equals some, I don't know, sigma k, and then this S equals tau sigma k. So this is just a linear scaling. And then we also chop off a tiny bit here. Don't forget this part. Or more or less forget it. And then we find by a procedure that Mantelidis and Chain suggested, and then was later refined in the series of papers I mentioned in various directions. And we have to refine this part even further. You can construct a positive scalar bridge that here looks like a cylinder, but you should think of it more as opening up in between. That matches them, so everything is smooth, has positive scalar curvature all the way up to this surface here, and is parameterized by this S parameter with S2 cross sections, and is fairly symmetric across those cross sections. And really, in this bridging procedure, there's a lemma that tells you that you can always do that if the two surfaces you want to bridge between have certain properties, and we don't need to change much about these properties from what was known before, but we do need to perform the bridging not in a way that says there exists a bridging profile, so a radius profile where how you can bridge this with positive scalar curvature, but we need to get it extremely precise so later we can get estimates along the sequence of this bridging procedure. And also there's a modification procedure involved here to make this, the bridging only gives you C11 regularity here and C11, so you bridge all the way down to here. C11 regularity down there, and then later you want to modify, which is the whole point of making the scalar curvature positive in this region here, so that you can modify there without destroying the non-negativity of the scalar curvature. And the modification, we also need to choose a precise modification, not just any, and make it extremely well controlled in terms of the sequence parameter k, or the epsilon parameter in the initial construction, if you will. So this is where really the hard work happens, this bridging procedure, that we can adjust that to get a convergence result. And then in this scenario, Sk goes to infinity, or alternatively, as this parameter epsilon goes to 0, it doesn't need to be a sequence, could also be one parameter family. In the color, so the blue region in the picture up here, in the color becomes a finite length cylinder. Although cylinder should be in quotes because the cross sections are only round after this parameter theta here. And to the left, so for smaller s than this theta sigma k, there will be a threshold where they're not spherically symmetric, and they will be spherically symmetric to the right of that threshold. So it's not really a cylinder, but all the cross section of constant s will have the same area. So in that sense, it's a cylinder. And once it's round, it's of course a usual cylinder. So we'll have 0 sigma k crosses 2 is where the color lives, and these sigma k's converge to some number s infinity, which is bigger than 0, and actually is not just bigger than 0, but turns out to be in some sense corresponding to a Schwarzschild radius of 2m infinity. It's not the value of S0, but that's what it corresponds to. It's a positive number. And the area of each of the cross sections, S cross S2, has area for pi r naught squared, for S0 less than or S less infinity in the limit. Okay, so we can draw this limit as this G0, which is S equals 0, all the way to some S equals infinity. And it's spherically symmetric from somewhere onwards. And all these cross sections have the same area, and also all of them have mean curvature equals 0. So in particular, as I said in the beginning, and as I showed you in the Lisa-Omani spherically symmetric example, it's the inner boundary is only weakly outward minimizing and is hiding behind a lot of more minimal surfaces of the same area. And then the Schwarzschild part, which was yellow before here, which looked like a Schwarzschild cut off at some value sk plus delta k, and then bent inwards in spherically symmetric form to some value sk, turns out to become a full Schwarzschild, which is attached here. So this is Schwarzschild of mass m infinity, which is the mass that was the limit of all the masses, which was sharp for the Penrose inequality for this metric here. So m infinity is square root of the area of S2 with respect to G0 divided by 16 pi, all the way down to the horizon.
Carla?
Yes?
You have 5 minutes. So.
Thank you. And all the bridging, and that's where I'm going to end, collapses. So this is no bridging area left. Bridge disappears. Okay, so thank you very much for your attention, and I'm curious to get questions.
Thank you so much, Carla, for the nice talk. Please, if you have any question, unmute yourself and feel free to ask.
I have a very simple question. Maybe everybody else knows, but I don't. What if you take that interior thing to be round, and then you assume that scalar r is equal to 0, and you want to look at all the metrics such that the Penrose inequality is saturated, as you say? Does that follow that you have to have a simple Schwarzschild of Schwarzschild slice on the interior, on the exterior? Does that follow from that?
Let me try to understand I'm not sure I understood your question. So let me say, if G naught is exactly round,
yeah,
then all the construction will lead to a spherically symmetric object, which is a finite length cylinder which is round.
Yeah.
And attached to a Schwarzschild exactly at the horizon.
But what if you assume that scalar r is equal to 0?
The scalar
everywhere?
curvature. In this method, I cannot do that because this scalar bridge, this color one constructs already has positive scalar curvature by construction. But
right.
there's work building upon Bartnick's quasi-spherical approach, which makes a similar construction as this and asks related questions. And off the top of my head, I cannot say. I think Pangzi Miao was involved in this, but I'm not sure about all the co-authors. Maybe someone can help me. Armando, maybe.
Okay, thank you.
Hi, Carla.
Hey.
I have a question.
Go ahead.
In your description, you say the A has to be very carefully chosen, this factor A. You mean specifically to your work, your current work, it has to be carefully chosen?
Yes.
Could you make any comment about that?
Yes. You can, if you take the form of this metric ansatz here, then you can just compute the scalar curvature in terms of all the things and that are involved, in particular the eigenfunction and the flow g of t of metrics that you have. And then the estimate on the scale, if you compute the scalar curvature, because both the eigenfunction u and the flow g of t depend on time and on the points on the sphere, you have to take a lot of suprema and infima, and you get the eigenvalue lambda 1 in, which is why you want it positive. So you get supremum also with the eigenvalue in time. or infimum, if I don't remember the sign. And you need to pick A depending on all those quantities so that it's positive. So what's found in the series of papers I mentioned is that there's a lowest value of A depending on all these quantities that you can pick, and all larger A will also do the job. And what we had to do is we had to check if this persists, if you allow the epsilon to change now. And in fact, it turns out that there is an uniform and epsilon lower bound that you can pick for all the epsilons, and you don't have to make the A depending on the epsilon or on the sequence index K. And it depends on the first derivative along the flow, this G prime, of which we set the trace to be 0. On this, the absolute value of this G prime, and which is a constant alpha introduced by Miao and Xie. And it also depends, as I said, on the eigenvalue and the eigenfunction. You could use a different type of flow rather than the uniformization flow, say for positive Gauss curvature, and then you could get rid of this U of TP term, and then the estimates would become a little bit simpler, maybe. But you would only prove it for a smaller class of G0s.
Thanks.
Sure.
But does your A depend on epsilon at the end?
No, at the end, no. I mean,
So it's large. It's very.
It's large. It's uniformly large. Yeah.
Okay, I see.
We could take it smaller if we make it dependent on epsilon. But if we are fine with making it large, we can pick it uniformly.
Also about your sequence was epsilon equal 1/k. So,
yes, so we really have a one continuous parameter families in epsilon, but for wording it more easily, I wanted to word it as a sequence, but it's really a one parameter family of epsilon dependent metrics which converge to this gamma infinity uniformly in epsilon.
Oh, because I remember epsilon should be very, very smaller than 1, so.
Well, it depends on the initial data and on the flow that you pick, how small it has to be.
Okay. Any other question?
Not a question, but actually I was just thinking about this question of Jim's before. So the idea was trying to say, can you make this thing so that it's complete scalar 0, if I understand correctly?
Yeah.
I'm not super familiar with it, but there was this work from Locamp a while back about sort of, pushing scalar curvature down, without changing it too much. I can't remember exactly how you do it, but I think you can sort of basically push the scalar curvature down to 0 on all of these, approximating things. And then probably in the limit, you would get something with 0 scalar curvature. I'm sure there's someone here that's more familiar with this work than me, though. Like I think you can push the scalar curvature down to 0 and the metric changes, the metric stays close in like C1 alpha or something.
Would that be enough to keep the inner boundary minimizing though? And minimizing strictly outward minimizing? Minimal strictly outward minimizing?
That's the bit that I was sort of sticking on. I'm not really super familiar with the work, but I'm curious now. I think it should though.
Okay.
One could also ask about stability. What if you look at metrics, where the you're almost saturated? Do those metrics is a topology in which those metrics must approach the slice of source shadow or something like that? I don't know that much about that kind of thing, but curious if anybody else might know about that.
So all that seems to happen is that everything works fine outside the outermost minimal surface, yeah? In the limit, because the boundaries are outermost minimizing in the sequence, but somehow behind the outermost horizon, things can happen in the limit. That seems to be the consistent picture, unless you impose such a uniform, smooth inverse mean curvature flow condition as Brian Allen does, for example, or maybe other conditions like that will work too, that you can somehow prevent that from happening, which is somehow that the horizon splits into a whole cylinder of horizons, yeah? So if you have this uniformity condition, you somehow keep the horizon together in one piece. And if you lose this uniformity, your horizon can spread out into this cylindrical-like structure. That's what seems to be happening. And I'm not sure if that's even weird, or if maybe that's even what we should have expected, or I don't know.
Any other question? Okay, let's, if there's no other question, let's thank Carla. Thank you, Carla, for your very nice talk. And
Yeah, thank you. Nice talk.
Thanks, Carla.
Thank you. Yeah.
Thanks.